Hey everybody, I hope you're having a great day so far. My name's Adam Patterson. I'm going to be presenting on the Lorentz force and the right-hand rule, and hopefully we'll be able to learn some new things today about it. So, for basic understanding, so that we can better understand the Lorentz force as we talk about it in the right-hand rule, I thought it'd be best to start with some basics about magnetism and magnetic fields. So, what causes all magnetism? That would be current, the flow of charge. And the magnetic fields that come from these things only exert forces on moving charges. So the charges cannot be standing still. So today we're only going to be talking about moving charges. And for example, other magnets that all have moving charges within them would have a force exerted on them. That force is what we're going to be talking about today. And something important to understand as well is that magnetic force is more complex than a Coulomb force. So don't be discouraged if you're not getting it right away. It can take some time and practice just to really get it down. Okay, so we can sort of start with the basics here. What is the Lorentz force? So simply put, it is the force acting on a charge that is moving through a magnetic field. It's otherwise known as the electromagnetic force, and it's measured in newtons. So pretty much how it works is that a charge is moving at a certain velocity, and as it moves, it creates a field around itself. And that field is going to interact with surrounding magnetic fields. That's sort of a hard to understand definition, but I think we're going to get it better as we talk more about the quantitative and qualitative aspects of the Lorentz force. So let's get into that. So the quantitative analysis of the Lorentz force. There's really just this one basic equation on top there. The bottom one is just a derivative of the first one. I just solved for B. So let's talk about the variables in this equation. Um, F is the Lorentz force, measured in newtons. Q is going to be the charge, which is measured in coulombs. The velocity of the charge is V, measured in meters per second generally. B is going to be the strength of the magnetic field. But something to note about this Tesla, which is the units they are measured in, is that Tesla is very large. So in the book, they talked about how the largest superconducting magnets are around 10 Tesla. So if you just keep that in consideration as you're solving problems, because they can use different units of measurement, such as a Gauss, because it's smaller. And then the theta will just be your angle between your V and your B, your velocity and the strength of your magnetic field. Now with all that, we can find the Lorentz force. So I thought it'd be a good idea to maybe go through a quick example of how to do a math problem using this equation. So this is just a problem from our homework from the OpenStax physics book. So let's go through and read it out. An electron moving at 2.72 times 10 to the third meters per second in a 1.25 Tesla magnetic field experiences a magnetic force of 1.4 times 10 to the negative 16 newtons. What angle does the velocity of the electron make with the magnetic field? Now, if you remember, that angle, which is theta, it's literally just asking you, what is theta? Because if you look back in this slide, theta is the angle between V and B. And it's asking what is the angle between V, velocity, and B, the magnetic field. So with angle, we can have two answers actually, because there will be two answers between 0 and 180 degrees. If you think about a unit circle, all that is positive. We'll have a positive y value. So it's pretty simple how we can solve this. We start with our basic equation, F equals QVB sine theta, and then we simply solve for sine theta, because we want to get that theta alone, because that's what we're solving for, right? So we take this sine theta in step 2, and we're just going to plug the numbers in that we have here. So we have the Lorentz force, which is given to us by it says magnetic force, so 1.4 times 10 to the negative 16 on top. And then you have the charge, you have got the Tesla and the magnetic field. So with these questions, with these variables, we are able to solve for 14.9. So that's how we got that answer, by taking the inverse sign of that right-hand side of the equation. After we take that inverse sign and get 14.9, to get the 165.1 degrees, all we do is we take 180 and subtract 14.9. And this way we're able to get our smallest number and our largest number values for theta. I hope that made some sense to you. Okay, so now we're going into the qualitative side. This side is a little more fun in my opinion, and I really enjoy this rule and that it holds up in any situation. So this right-hand rule deals with the direction of the magnetic force, the magnetic field, and the current. So to really find this force, there's some pretty easy steps here. So it's 3 steps. Take your thumb and you're going to point it in the direction of the current, I, or V, sometimes referred to as V. So this current is just going to be an arrow on the page. So you point it up in the direction wherever that current is going. Point your index finger in the direction of the magnetic field. So that will be B. And once you have those 2 fingers pointed, you just raise your middle finger so that it's perpendicular to your palm. And wherever that finger is pointing, that is the direction of the Lorentz force, or F. Important side note, this is in relation to protons. So this would give you the exact right answer if you're talking about protons. If you're talking about electrons, however, you just simply take your answer and flip it. It's going to be the opposite of a proton, because positive and negative. I guess that makes sense intuitively. So let's get into some examples so that we can learn how to use this right-hand rule. So let's start with A here. That V line is going to be the current. Well, I guess before that, let's read the directions here. In what direction is magnetic force exerted? So we are looking for F. We're looking for the Lorentz force. But to be careful, because I listed as well that we're going to answer C and E in terms of an electron. So we'll watch out for that as we get there. So for letter A, current is going to be going downward. So we point our thumb downward. Now we see that B is coming out. So we point our index finger at ourselves from the screen. And then we just simply put our our middle finger pointed out, perpendicular. And where is it pointing? Should be pointing to the left. Okay. So let's go through another one. Current going up. So our thumb's up. We got the magnetic field going to the right. Now point your finger, your middle finger, perpendicular. It should be going into the page. Now let's work through this one. So C, remember this one we're going to flip our answer because we're answering in terms of an electron and not a proton. So let's look at it. V, current, is going to the right, thumb to the right. We are pointing our index finger in and our middle finger is going where? Should be up, but we're going to make sure we make it opposite. So it is down in terms of an electron. Up in terms of proton, down in terms of an electron. So here with letter D, we're going to be taking our thumb, pointing to the left, index finger to the right. Oh wait, really can't do that, can we? We'd probably break our hand if we tried to point them those directions. So if we have a situation like this where the current and the magnetic force are going in different directions, or the magnetic field are going in different directions, there will be no force exerted. That's just a good thing to remember there. Okay, so letter E, we're going to answer this in terms of an electron as well. So let's point our thumb in to the page, into the screen. And now our current is going upwards. Okay, current going inwards, magnetic field is going upwards. So go ahead and point your middle finger out. Where is it pointing? Is it pointing to the right? That is an answer of terms of a proton. So an electron would be to the left. Okay, I think you guys got it. So this last one, current is coming out of the page, magnetic field is going to the left, and our finger is pointing down. So I hope with all these examples you were able to really nail down how to use this right-hand rule. It's very handy. Um, it it won't fail you, really. It'll get you the right answer if you need to know in what direction any of these three things are going. And that is all I've got for today. So thanks for tuning in. I really appreciate it. And these are just some of the references that I used for making my slides. So thanks everybody. I hope you have a great day.